Alright, so if this is the slope, change in y or change in x. If I solved it for y, it'd be slope. Can you see this? Is red okay?
Yep.
Minus x sub 1 equals y minus y sub 1. So y is equal to y1 plus the slope, x minus x sub 1. Alright, all I've done so far is algebra, right? We're going to magically turn our algebra into calculus.
Magic. I wish this was magic.
This I will call f of a.
What's A? That's what he's calling it.
X of 1 is, oh, this is not f of a. This is the linearization. This is a, that means this is f of a. Slope, we can call that f prime of a. Okay, so the point is a comma f of a. If I plug in a comma f of a into this formula, I get this. Okay, so all I've done is written the algebra in the calculus version. So this right here is
What does L mean?
the linearization. Well timed, Wilson, nice job. Alright, so what is a linearization? All it is the equation of a line tangent to the curve. Have we done that before?
Yep, like 1,000 times.
Right, like that's pretty fundamental to calculus. You need to be able to find the derivative, and eventually find the tangent line or equation line tangent to the curve. Alright, so we'll do an example. We'll say f of x is
7x squared.
7x squared minus 3x.
Yes.
Alright, so if we want to use our linearization, we're at x equal to
3.
3.
Do 2, it's a big number. Oh, like we just square
2.
it. Thanks.
Alright, so we need to find f of 2. So when it says x equals 2, think of it as a equal to 2. So I know f of 2 is 28 minus 622.
Wow, that was
I need to find f prime of 2, so we need to find f prime of x. So f prime of x is 14x minus 3. So f prime of 2 is 28 minus 3, which is 25. Okay, so now our linearization is f of 2 plus f prime of 2 times x minus 2. Okay, what did we just find?
Linearization.
The tangent line at 2. Okay, not a real workable form, right? So if you wanted to put it like slope-intercept form, it'd be 25x minus 50 plus 22, so 25x minus 28. That'd be our answer. Alright, so what if I asked you before today to find the equation line tangent to the curve at 2? Could we have done that?
Yeah. It's a lot hard.
Actually, it's easier, right? Well, I don't know, it's about the same. So all you'd have to do is find the derivative. We have that. Find the derivative at 2, so f prime of 2 is 25, and then you have to mx plus b it, right?
Here's my favorite part.
So my slope is 25. Your x is 2. Your y, well, you have to find that. That's where the f of 22 comes in.
E.
Plus b. So b is negative 28. So my line is 25x minus 28.
I was like, it's right down there.
What's the obvious question?
Why would you do this?
Exactly. So why would you have to do linearization? So you'll be asked linearization it leads to what we're doing next, which is called Newton's method. But in the future, if you were ever asked to find the linearization of something,
You can do it either way.
do it this way if you don't remember the formula. And a lot of people will not remember this formula. True? You might remember it in this chapter, you might remember for the quiz and the test, but 2 months from now, if you're asked a linearization problem, you're not going to remember if that's x plus a or x minus a. You're not going to remember if that's plus or minus. Right? You could generate it from our slope equation, but it'd be easier just to find the equation line tangent to the curve at a point. Okay? That's the way I would do it. I don't, like, this is not all that easy to remember. But that's linearization. Okay? So why do we do a linearization? It's, if we have something really difficult, as far as the equation, really gnarly, and it goes like that, and we want to use, we're only looking in like maybe this interval right here. So if you zoom in on this between here and here, rather than using f of x, which is x to the 7th plus a whole bunch of other stuff, we could just say, well, this line right here would be a pretty good approximation, as long as the interval is small enough. Like, this would not be a good approximation once it goes beyond this point and that point, but the linearization simplifies things as long as we have just a small interval. Okay, so if we go back to how easy we're going to be able to graph this. It's x, 7x minus 3. So it's got x-intercept at 0 and 3/7. That's not too bad. And we're at 2. 1, 2. So here's my graph. Alright, so there's f of 22, that's 2 comma 22, right? Alright, so the original is a parabola. We did a linearization, so we created a line at that point. So a question that the book will ask you, or on the AP exam, they'll ask you, use the linearization to approximate L of 2.1. And compare it to the original. How close is it? Well, it's not going to be exact, right? Because we went a little bit to the right, so it's going to be more or less. Our linearization is going to be more or less to our original.
Less.
Is the green line at 2.1 going to be bigger or smaller than the blue parabola?
Smaller.
It's going to be smaller. It's below the parabola, right? Okay, so if I plugged 2.1 into our linearization, I got it'll help.
Wait. Oh, 2.1.
What's 25 times 2.1 minus 28?
That was like the 52.
Minus 28 is 24.5.
52.5.
What is it?
24.5.
24.5. And what is f of 2.1?
Go Cap.
$37.17. Is that right?
Oh, is it?
Really?
Oh, he didn't round. It's 37.2.
It is, huh?
Oh, I don't know.
7 times 2.1 squared minus 3 times 2.1?
Yeah.
People take out their calculator.
That sounds a little better.
Yeah.
So you got? We'll go with that.
Yeah, she's right. I don't know what Hal's doing.
24.57. Alright, so our linearization compared to our actual, that's a decent approximation, right? Why wouldn't you use the original? Why would you ever dumb it down to get a worse answer? as far as to save effort in energy and processing speed, if you're doing it on a computer, and if it's close enough for our, like if we recognize that the amount of error is okay, and we want to decrease the amount of time your computer's going to have to process, then you would just simply use a linearization. Okay, questions on linearization? There's another way we can approximate things I'm going to talk about next. It's 1 plus x to the k can be approximated as 1 plus kx. Okay, so we worked all our lives trying to get the exact right answers, and now we're saying, as long as we get close enough, and here's another close enough. Another way we can approximate this. So if I have like 1 plus, let's say I have 1.04 to the 5th. Well, that could be written as 1 plus 0.04 to the 5th. So this can be approximated as 1 plus 5 times 0.04. You see that? Using the formula?
Oh, it's almost that.
So 5 times that is 2, 1.2. And what is 1.04 to the 5th?
1.21665.
So that's exactly 1.21665. And we got a pretty good approximation as 1.2. Why would we do this?
To save processing power.
To save, yeah. If we don't want to put the energy in actually figuring that out, this would be a decent approximation.
It's pretty much like whatever amount of like significant figures you need for like whatever you're doing. So if you don't need as many significant figures.
Right. Yep, that's a good way of putting it. Yep. You might have the square root of 1 plus x. It has to be written in this form, so you'd go 1 plus x to the 1/2, which then becomes 1 plus 1/2 x. That make sense? Okay, so you're going to have to, the problems in your assignment, you're going to have to manipulate it a little bit, but you have to have a 1 here, plus a number to a power. Okay, so that's the other way we can kind of approximate. That's not a linearization, but that's just an approximation. Alright, so far so good? Alright, so the last thing we're going to talk about, well, maybe not the last thing. The next thing we're going to talk about is Newton's method.
Hey, that's a linearization. That's a cow.
Alright, so I just made my linearization 0.
Why?
Alright, so that is Newton's method. That's how we generate it. We're just, what is Newton's method? It allows us to solve,
It's
kind of a bad week for measures.
Ooh, you made both of those. What was a cat?
It allows us to solve a problem like this. Do we know how to solve that?
Yeah. Well, what are you asking? You graph it, and then you look
Solve
at where
for
it
x?
crosses.
Do we know how to solve that?
You watch where it crosses the x-axis.
Right, so right now the only way we could do that is with a calculator, right?
What if you did it?
Until now.
Wow.
That's right. Okay, so Newton's method. We have a curve that looks like this. What we need to do is, so this is our answer. Like if this was x cubed plus x minus 2. So we need to find a point somewhat close to that as our initial a. Okay? Then we find a linearization at that point. So we're going to find the equation line change of the curve at that point. Okay? And we find when that's 0. And we use that as our next a. And we're going to find another linearization at that point. And we're going to keep going until we get to that exact answer. Okay? This isn't a very good drawing. Like, I should have done it a ways.
So the graph doesn't make sense either.
It's fine.
Okay, so here's the process. We need an initial a. So for this problem, if I plug in 1, I get 0. Okay.
You can hear 2.
1's actually an answer, right? So minus 3 now.
Oh, changes.
So if I plug in 1, I get negative 1. If I plug in, should I go a little bit more or less? How about 1.5? 1.5 cubed is
6.
I almost thought about that.
3.375.
3.375 plus 1.5 is like 5. We're going the wrong way. So how about 0.8? We'll try 0.8 as our initial a. I hope this works. So to find our next a, so I'll call this x sub 1. To find x sub 2, we use our x sub 1 minus f of x sub 1 over f prime of x sub 1. So to find our next one, we can do 0.8 minus f of 0.8 divided by f prime of 0.8.
Wait, isn't that just 0? Wait, never mind. What? Well, when you say
Okay,
f prime,
so f prime, we need a derivative.
oh, I'll do it.
It'd be 3x squared plus 1, right? So it is 0.8 minus
Oh,
0.8 cubed plus 0.8 minus 3 over 3 times 0.8 squared plus 1.
you waiting for one of us to do that?
Do it in your head, Mr.
Okay.
Boy.
So this looks icky, right?
Yeah.
And especially since it's probably going to take 6 times of Newton's, give or take, in order to figure out what our answer is. That's really icky. Okay, so let's use technology.
I am.
Let's grab your calculator.
Do this one.
Oh, it's
It's all-
negative 0.57. Wait, I need to
program.
five.
Because it runs.
Actually, that's not right. Actually,
All right,
this is
let's-
something else.
Or that's
Store
the right
0.8
side. Yeah. It's 0.5.
in alpha A. Store 0.8 to alpha A. So type in 0.8 stow alpha A. Or it might automatically, does it automatically do an alpha?
What's stone?
Store. It's right above on.
Oh, I found it.
Oh.
A.
Everybody have A as 0.8? Okay.
No, wait. What? You just said a bunch of.
Oh, I gotcha. Okay, so
Oh.
what you do?
So A is now 0.8 on your calculator, right?
Yes.
So,
Okay, so let's type in
then 0.8,
A
then A
minus
alpha A,
parenthesis
and then
A
so now whenever you
cubed
press A,
plus
it will give you
A minus
6
3
plus A,
parenthesis
it will give you
divided by parenthesis 3A squared plus 1 parenthesis.
Oh, I wish I would have known this earlier.
Hit enter, what do we get?
1.38.
Okay, I want every decimal you have. 1.38.
378. Oh, you got it?
Did you just make those up?
Oh,
I
the
listened to what
first
she
one
said.
was a 37. 3780.
Oh, it starts like right there.
Yeah.
Okay. All right. Now we have to do it again.
So set that equal to
But
B.
let's use technology. Let's store that in for A now. So store it A. So you have that in for A now. Right?
7, 8.
Now,
Oh, so you just go up to the top and like.
hit second enter into the retrieve our formula that we already wrote in,
Whoa.
and then hit enter.
Okay.
How will we know when we get there?
Oh, do you have to wait?
When you get the same number
Second
twice.
It's 1.213411663.
Faster this time, please.
1.213411663.
That's
I didn't get that.
3.
Oh yeah, I don't think I typed in my formula right.
We got it, everyone.
Thanks, Wilson.
But I got
What do you got?
1.229483817.
83817.
Yeah.
All right. Store it. Second enter. Enter.
There's your 1.213583053.
Is it?
Yeah.
Okay. Store it. Second enter. Enter. I hope that we get the same number.
Yes. Oh,
Getting
wait.
closer.
It.
Is it getting closer?
Yeah.
Okay,
It's-
good.
Yeah.
I'm doing my job right. It was the exact
Excuse me.
plus.
Okay, 1.21 I hope. 3583.
Yeah, it's right. Oh, did you want the next number? Yeah, eventually it goes to 1.
No.
Okay.
No, if I gotta read. 0.21341.
So erase 5, 8.
Okay. Yep. All right, Rhea, you're now my number woman. All right.
213411682. There.
Okay. So I said it would take around 6 tries. I think it's going to take a little more than 6. So store. Second enter.
Oh, and then you get 1.213411663, and then it repeats.
663.
Yeah.
Okay.
And then the next time it repeats.
It's
That's
the
what I
same thing?
told you. That's what I told you.
No, like after that. Yeah, it repeats.
So the 7 is the exact same. number.
Yeah.
Okay.
Yep.
So it did take us 6. Okay. So once you get the same number twice, we know we got our answer. Let's graph this equation, y equals that, and calculate the x-intercept. The 0 or the root.
Gotcha, boss.
What time is this?
Oh my gosh. Never enough time.
Usually I'm the one asking that.
In the year of 2016, it ends out.
So if you calculate the 0 at that point close to 1, do we get the same number?
Oh, the window's way
It
off.
rounds it, yeah.
So we just solved that. We found the x-intercept where we solved that equation using Newton's method. So one downfall is you need to be able to find a number close enough. If this has an x-intercept over here and I choose this as my number, it's going to all of a sudden converge to this point. So we have to get it close enough. If I have this pretty close, this will shoot it across, and this will shoot it across, and then this will shoot it across. We'll talk more about it on Monday. But